Welcome to Lesson 4 in our redox unit. Today we're going to cover redox titrations. So recall from last time, we were able to prove that this reaction was possible. Well, hopefully you were able to prove that this reaction is possible from the reactivity series. So recall that strength of reducing agent increases in positive correlation to increasing reactivity. So because of that, we're able to see that zinc is able to displace copper because zinc is higher up on the reactivity series, thus able to form zinc sulfate and copper solids as products. We're able to see from this reaction occurring that copper is deposited at the bottom slowly as the reaction of zinc and copper sulfate react to form zinc sulfate and copper. Now let's move on to redox titrations. Recall last lesson as well, where we talked about whether or not acid-base titration, such as a neutralization reaction, is in fact the same for redox titration. And the solution to that one that you guys answered on Nearpod is that no, acid-base titration and redox titration are separate. So neutralization reaction occurs in acid-base and does not occur in redox titration. This is because acid-base titration really focuses on not just the acid and the base, but also the proton transfers. So when something is neutralized, you have anions and cations in the reactants, but because they're neutralized, they might form an ionic compound, or they might form a compound that did not actually change in electrons. So no electrons are actually transferred. Because of that, that is not a redox titration. Redox reaction, however, is between oxidizing and reducing agents that we covered in Lesson 3. Electrons are transferred from reducing agent to oxidizing agent, different from acid-base when they talk only about protons. Here are 3 titration methods that we are going to cover today. Some examples of redox titrations, just so you get an understanding of why this is important, is, for example, we can test the sulfur dioxide content in wine through redox titrations. We could form a lot of household products, from toothpaste that you use to bleach, detergent, fertilizers, etc., all through redox titrations. So redox titrations are actually kind of the fundamental of everything that we use as consumer products. And here are 3 examples and 3 methods of titration. We're going to start off with the analysis of iron with manganate 7. So redox titration, the analysis of iron with manganate 7. Let's take a look at this problem first. All iron in a 2-gram tablet was dissolved in an acidic solution and converted to iron 3+. This was then titrated with potassium manganate. The titration requires a 27.5 centimeter cubed of 0.1 molar of potassium manganate. Calculate the total mass of iron in the tablet and its percentage by mass. Describe what would be observed during the reaction and how the equivalence point can be detected. So because this is a titration similar to acid-base titration that you guys covered last unit, we also talk about equivalence points when we talk about the interaction between various reactants. We're going to start off by noting the oxidation and the reduction half reactions. So because iron is converted from iron 2+ to iron 3+, this, of course, is the one being oxidized. Therefore, the one being reduced naturally is the manganate. So after, again, conducting our rules of forming half reaction equations, we're able to form the reduction equation for this particular chemical reaction. Now, we need to calculate the total mass of iron in the tablet and its percentage by mass. So look at what is given to us in the problem. They gave us 2 grams tablet, 27.5 centimeter cubed of 0.1 molar of potassium manganate. So, with these three data points that we are given, we can extract 27.5 and 0.1 molar of potassium manganate to use to calculate the total mass of iron. After writing the overall balanced equation by eliminating the electrons, we're able to come to this overall balanced equation. From this balanced equation, we can calculate various molar ratios. So first, let's calculate the moles of manganate ions, which are given in the problem. This gives us 0.00275 moles of manganate. From this, we're able to calculate the molar ratio between that and iron 2+, and the molar ratio is 1 to 5. So because of that, we're able to calculate iron 2+, the number of moles in this specific reaction. So we multiply the blue 0.00275 moles by 5 to calculate iron 2+ moles. Then from that, we calculate iron has a molar mass of 55.85 grams per mole. And from that, we're able to calculate the mass in grams of iron. From the previous slide, I extracted the overall balanced equation and the number of moles that we were able to calculate, the number of grams of iron, and the last part of the problem asks us the percentage by mass of iron in the tablet. We are given 2.000 grams of the tablet, and iron comprises of 0.7679 grams. So from this, we're able to easily calculate the percentage by mass of iron in the tablet, and that is approximately 38.4%. So let's take a look at the reaction again. So manganate in acidic solution acts as an oxidizing agent, right? So it in itself is the one being reduced, like what we mentioned in our reduction half reaction equation. This has a natural color change because it itself is an indicator. The manganate turns from purple to colorless, and the iron here is the reducing agent, the one being oxidized from iron 2+ to iron 3+. So the color change to us when we carry out this titration is going to signal the equivalence point. And these would be the two colors that change from reactants to products. So now let's take a look at the second redox titration. Second redox titration is iodine-thiosulfate reaction. So we first start with sodium thiosulfate, and this gives us the thiosulfate ions, and we have something like potassium iodine in the solution. So what we do is we first have iodine, we mix that, we titrate that with sodium thiosulfate. After this titration, we add a little bit of starch indicator, so we don't titrate it until completion just yet. So right before completion, we add in a little bit of starch indicator, and this is going to change our solution to a blue color. And as this blue color persists, the iodine is going to convert into iodine ions in the product. So as they convert to the product as iodine ions, this is going to change the color from blue to colorless. So the starch indicator acts as a form of indicator to show us the equivalence point and when the reaction has reached completion. So we start off now looking at the chemistry behind it. We start off with oxidizing agents using something like potassium manganate or any of the other oxidizing agents. And we reacted with iodide ions. This is going to form iodine, and this is the iodine that we are going to use in our reaction with thiosulfate. This iodine is then titrated with sodium thiosulfate, And because iodine is turning into iodide ions, we know that that one is the one being reduced. And so sodium thiosulfate, the thiosulfate ions are naturally going to be the one being oxidized. We then write out, again, our half reaction equations to figure out the oxidation and the reduction. And then we see the color change from blue to colorless by adding in the starch indicator. And this tells us, again, that the equivalence point has been reached. And here's the final equation. So with sodium thiosulfate and iodine, this forms iodide ions and tetrathionate. So tetrathionate. Our third and last redox titration we're going to look at is the Winkler method for calculating dissolved oxygen. This shows us the water quality indicated by dissolved oxygen. BOD is biological oxygen demand, and this is the degree of pollution. So when we have more BOD, then it means we have more degradable organic waste in water. If we have more degradable organic waste in water, then it means we have lower levels of dissolved oxygen. What does that mean exactly? So all of this means that when we have higher BOD, we have more phosphates and more nitrates, which harm the biodiversity in lakes and in bodies of water. So when we have nitrates and phosphates, they're stuff that persists in things like detergents and things like fertilizers. And that then forms blooms of algae. So in bodies of water where you see blooms of algae, there's probably high BOD where there is lower level of dissolved oxygen. So because there are more algae, then it means there's something called a phenomenon called eutrophication, and this means that biodiversity has decreased because you have lower levels of dissolved oxygen. So this in itself is an environmental concern that we need to consider for, and the Winkler method helps us calculate the BOD of water quality. So now let's take a look at the Winkler method and how we can calculate BOD. So we first start off with dissolved oxygen reacting with any kind of a basic solution with manganate salt. And so in this basic solution, we're able to form, as you see, manganese ions from +2 to +4. So here, manganese is being oxidized. In the second step, we react this +4 with acidified iodide ions. And this is going to produce manganese 2+, iodine, and water. With this, we're then able to use this iodine, and from the thiosulfate that we just talked about in the previous redox titration, we can follow that method to titrate iodine with sodium thiosulfate to form iodide ions, and once again, tetrathionate. So my next question is, what exactly would be the thiosulfate versus dissolved oxygen molar ratio? Take a look at these three equations. So let's work backwards and start looking at the molar ratio between thiosulfate and iodine. So from this 2:1 ratio, we can calculate iodine and manganese dioxide. From the second equation, we can then calculate the molar ratio between oxygen and manganese dioxide and iodine. The molar ratio is 1/2 to 2. Therefore, so 1 mole of oxygen in water is 4 moles of thiosulfate.